Okay, so last section is about Terra series. Remember, we can express some elementary functions, almost all, as power series over some interval, but cannot be over the whole domain, where the function is defined. Okay, because the interval must be symmetric about the point. Okay, so that means if you have a elementary function defined on some interval, if you can choose the middle point of the center of the interval, that's probably okay. You can represent this function, uh, over that whole interval. But if the number you choose not in the center, then you can only represent that function on a portion of the domain. Okay, so that's what I'm saying. And on the other hand, okay, there are many functions can be defined by power functions, a power series, but that's not can be expressed as an elementary function. Okay, so think about So usually, if the function let f of x, maybe I don't know, be a function on the interval I. Okay, it depends where it is. Okay, then in general, okay, you can. So this is interval. Okay, could be open interval, could be closed interval. That's just like that. Okay, now, for example. So it depends on where the point you choose. If you choose the middle point of the interval, then then you can express the function on the whole interval as power series. Okay, so in general, if you pick up point A, okay, then you have to look at which side is the small shorter. This is A, right? And this one is the largest interval you can symmetric interval above A, choose, right? Over that interval, you can, over over this interval from A minus capital I, A plus capital I, the function can be expressed as a power function. Okay, if the function is good enough, okay, if its function is an elementary function, okay, this is a domain. I is a, this is I. Okay, and this is I, and we can, in general, we can, pick up arbitrary point in its domain. Then we can find the largest in symmetric interval about A, containing I, and over that interval, we may able to express the function as power series. Okay. So in most of the cases, this is fine. Okay. Yeah. Now, a given power series at A, okay, it is convergent to some function over interval around symmetry about A. But that function sometimes can be expressed as elementary function. But that elementary function may be defined on a larger interval, okay? Not this one, okay? Not this interval from symmetric about A, okay? So, okay, this is what we learned. A function defined on some interval, okay, can be expressed at every point, nearby every point there inside the domain, you can express as a power series. Okay. Now, what we're going to do today is, okay, that's a picture. So what we're going to do that, if the function, given function, right, given function f of x on an interval, okay, and a point inside I, okay, interior point, okay. Questions, how do we know whether we can find a power series representation for the function? First question. Second question, if it is, can we find it easily? Okay. Now, the theorem, Taylor proved the following. Okay. Taylor says that, here's a Taylor theorem. Due to Taylor. Okay. Taylor says that if the function can be expressed as power series, okay, for x minus 8 less than some r, okay, then this Cn is going to be unique. It can be uniquely determined. Okay, it can be computed using these formulas. Okay, clear. So if the function defines some interval, a is a point. Yes, this is the picture is here, right? So this refer to that picture. Okay, refer to that picture. If a is inside the interval, okay, then if we assume that the function can be expressed as a power series for x close to a, then that power series cannot be arbitrary. Okay, right? Hey, don't forget, Black Friday is coming. Okay, I don't know where this message is from. But all right, so if the function has power series representation nearby some number, and that power series representation is unique, cannot be like a two different one. Okay, and the coefficients can be given by this simple formula. Now, how to prove it? The proof is, of course, we have to assume that a is greater than 0. Okay, r is 0, r is greater than 0. Otherwise, it cannot be. It's not true. So the proof is very simple. Just think about that. You first of all, f of 0, right? When you plug 0, suppose you have this identity. When you plus a for x, you will get a minus a 0, right? So only the first term left. Then you differentiate the function, and then the first term is 1. Okay, then actually is n x minus a to the n minus 1. Okay, and look at this. The leading term here is c1 times 1 and plus c2 times 2 x minus a and blah blah blah, right? So when you plug a for x, only c1 is left. Okay, when x equals 8, all the terms will be 0. So f prime a is going to be c1. Okay, we continue differentiate. So f the second derivative. The second derivative, the first term is gone, so n starts from 2. Okay, it will be cn n times n minus 1 x minus a to the n minus 2. Okay, if you really write down the details, it's going to be c2, and the 2 times 1 is 2 factorial plus c3, and you don't need to know here what is that. It's 3 times 2. Okay, x minus a. Okay, so again, for the same reason, if you plug a for x, you will get the only first term, and c2 times 2 factorial. So that implies c2 is given by this formula. And just keep it going. Okay. In general, the case derivative, okay, f of a k and n should start from k, and c n times n minus 1, n times minus 2, all the way. I think this is n minus k plus 1, x minus a, n minus k. Okay, the first term is when n equals k. The first term, the leading term, ck and k factorial plus ck plus 1, and some constant here, I don't care. That's okay. So when you plug a for x both sides, only the first term left on the left and right hand side. So finally, you get all the coefficients. So this implies ck equals. Okay. So we're done with the proof. And that means the end of the proof. So we determine the coefficient. Okay. So how do we find the power series representation? You just assume it exists. Okay. Then you get a power series, because if it exists, then it must be in that form. The only question left is whether it's converted. Okay. So here's the logic. Okay. So assume that f of x is always differentiable as many as you want. Okay. Near by a number a. Okay. Here's the point, right? If this has power representation nearby a, okay. If this, yeah, let me rewrite it again. If this for x minus a for some r, right? Then this is uniquely determined. Okay. My question is, just assume it's there, right? My question is, given function, you construct this power series. Number one, does a power series? Yeah. So this is just assumption. Ignore that part. Okay. Okay. Assume that f is differentiable with a, nearby a, right? Then we have a power series. Okay. Then we get a power series. Okay. This power series, right? Given function, as long as differentiable at a, right? Question one. Because we don't know that equal, we just say if the function is represented as power series, okay, then the CN must be determined. So there's only one candidate there. But it's possible this function is differentiable, but it cannot be represented by any power series. That's a possibility. Okay. So question is, given function differentiable at a, can it be represented by power series? Okay. So you have to solve the problem. You have to answer the following question. Okay. Given a differentiable, that means it's different. Yeah. Given differentiable function f of x nearby a. Okay. Question one is, because as long as differentiable, question one is this series convergent? For x minus less than r, for some small r. Okay. That's, we don't know. Second, if it is convergent, is it convergent to the function? If it is convergent, that's two questions here. Okay. Is it convergent to f of x? Maybe, right? That's it. Then you say must be convergent to f of x. No, that's not. You have to prove it, right? Convergent to f of x on the interval a minus r, a plus r. Then you can say I find the power series representation function. Okay, that's the logic, right? If the function is power series representation, then this must be in that form, no question. But question one is, how do you know this series is convergent? How do you know this series is convergent to the given function? You don't know. Okay. All right. So this series is called Taylor series. The reason has a name associated with that. Taylor figured out how. Yeah, Taylor prove something. Yeah, figured out how to check this series is convergent. How to check this series is convergent to the function. Actually, Taylor did the one step. Just find the condition under which the function is convergent to the series is convergent to the function. Okay. But anyway, let's go ahead to look at some examples. Okay, and I'm given function f of x. Okay, it is 1 minus x. I know I already have a character, right? And find the okay power series representation for the function at for this function nearby x equals 0. Okay, so that means that power series should be equal to something like that, right? And according to the above series, so we don't know, right? You know, supposedly we don't remember anything, right? Previous. I already have power series. So how do I find it? I need yeah. So I have to compute here. So if it exists, okay, question, answer, right? If such power series exists, then it must be this. Okay, so let's find it. I'm going to find it. But still, we don't know whether this is equal to that function. We just say if it exists. In most of cases, they're equal, okay? Okay, let's find out. Let's find this, right? F of x equals 1 minus x to the negative 1. I'm going to differentiate. I have to differentiate many times. When I differentiate once, I get a negative 1 minus x to negative 2, but times negative 1. So actually, there's no negative sign in front of that. And the same is true. If you find the second derivative, you get negative 2, 1 minus x to the negative 3, then times negative 1. So you get 2 times 1 minus x to negative 3. So still no negative sign in front of the quantity. So let's try again. It's 2 times negative 3, 1 minus x to negative 4, and negative 1. And I find that it's 1 times 2 times 3 times 1 minus x to negative 4. You know, you find some logic, find some pattern, yeah. So you can gradually find out, I just need to add a larger number to the front of 1 minus x, and here negative 4. Over there is just a third derivative. So I believe that the general one will be k factorial 1 minus x negative k plus 1. Okay, so that's my formula. You have to find the formula for the case order derivative. Then you calculate, it's complicated, right? Calculate this, which just equals k factorial. Then the series is going to be so that is going to be n factorial over n factorial x to the m. It's nothing but this. All right. Then say if it has power series representation, it must be in this form. Right? It must be in this form. We just find it. But question is still, is it convergent to the function? Then you have to think about, right? Yeah. My claim is it is convergent to f of x for absolute x less than 1. Okay. Why? Because we find a way to calculate this. Okay, it's going to be 1 plus x all the way to xm, right? It's going to be 1 minus x to the m plus 1 minus x. Okay, so it's convergent to 1 minus 0, 1 minus x, which is 1 minus x. And then this is just f of x when x is less than 1. Okay, so you have to prove that then. You do find a candidate, okay? And then you verify this. It's not only, convergent, but it's convergent to the function. All right, so Taylor trying to solve this problem in general. Okay. So here's Taylor's, Taylor's theorem. Okay. So given function f of x on some interval, okay, I, okay, that interval, I can draw the picture here. This is the interval. This is I, okay, and a point, maybe a here, okay, okay, and a is in I, okay. So we're trying to find power series representation for the function. We assume that, it's differentiable function, okay, over the whole interval. Yeah, differentiable. So I want to find the power series representation for the function nearby a. Okay. Maybe I do not, get not the largest possible a. So interval, but we can, if the function, okay, this is a minus r, a plus r. It's not necessary to just touch the end point, okay? So this is the interval. If, okay, the function can be represented by a power series over that small interval, right? Then the coefficients must be negative determinant. The question is whether the power series convergent to, the question is whether the power series you construct, okay, is really converging the function. What I'm going to do is I let consider the difference. K start from 0. K factorial f of k, a, and the x minus a. Okay, so take the difference. That's a gap for the function. Okay. Taylor says that I can estimate yeah, I'm going to modify the picture a little bit. Is actually consider closed interval. This is a D, okay, not R. And we can figure out R later. Okay. Taylor said that if the absolute value of this function is less than or equal to M for X minus A less than or equal to D. For X in that closed interval, okay, then he said that this error, the difference, is estimated by X minus A to the N plus 1, okay, for X less than or equal to D. All right, so of course it's going to be smaller than D. Well, this is smaller than D, right? So you can also just say that M N plus 1 D to the N plus 1. Okay. So as long as this converges to 0, right, I think that we should put N here. Sometimes it's not uniform, depends on N, okay, plus 1. So maybe it's better to put this. That depends on that. So anyway, we have this estimate. We have this estimate. So if you can show this converging to 0, then yeah. So if, okay, limit of this is 0, then what do you say? Then, okay, then this series is identically equal to that. Okay, for X minus A less than or equal to D, okay, uniform. Okay, the convergence must be absolute convergence. Okay, so now, yeah, this is a useful theorem. Okay, and we can use that to look at the following example. Okay, we use elementary functions. Okay, I just said that almost all elementary functions we know can be represented by a power series at any point inside the domain. Okay, my general statement is every elementary function can be represented by power series at a number inside the domain locally. Okay. And it's hard to prove because there's so many different type of functions there. Okay, but that's fact is true. So take a look at this series, this function. This function defines the whole line. Okay, this function defines the whole line. This one is defined the whole line, and yeah, find if it exists, find the power series representation of this function at, and then also determine over which interval they're equal, right? So let A to be an arbitrary point. Okay. So first of all, let me find its candidate. If it can be expressed as power function, right? Then I have to calculate the coefficient. So let me find the derivative first. Okay. So when you differentiate, you know that's always the same, right? No matter how many times you differentiate. That's a good part. Okay. So it makes it easier to find the general formula for the derivative. Okay. Then we get the Taylor series. Okay. We get power series candidate. Okay. Then we get the Taylor series. The Taylor series at A, which is going to be f of na mod divided by n factorial x minus a. This just is a candidate. Okay, it's not necessarily converted to the function. You have to prove that it's converted to the function. So let's compute it. And no matter how many times differentiates itself, so when you plug a for x equal a. Okay. 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 So it's the same number, right? You can even take the constant out if you want. So this is a candidate. My question is still if the function is x equal and over which interval equal to that, right? So we assume that x minus a is less than or equal to some d. Okay, for some d, right? I'm going to do some estimate. I'm going to estimate. Okay. This is going to be just e to the x. So clearly it's less than e to the d, right? Because x is no. Come on. It's less than some number. Okay, depends on. It's not just e to the x. Okay. This is going to be. Yeah, let me rewrite again. This is going to be e to the x minus a times e to the a. So you can take e to the a out, then e to the x minus a. So it's going to be less than e to the a, e to the d. Okay. So anyway, it's a plus d. So there's upper bound, universal upper bound. All right. Then according to Taylor's estimate, this is going to be less than or equal to. This upper bound is independent of n, right? So it's going to be less than or equal to e to the a plus d. Okay. Here's n plus 1 factorial. Then x minus a to the n plus 1. Okay. And I can say that this is going to be n plus 1 factorial, e to the a plus d, and that is d to the n plus 1. Yeah, this is a equal. But clearly this is going to be 0. Okay, I'm going to give it another argument. Okay, this is approach 0. Okay, for x minus a less than or equal to d. So it doesn't matter which d you choose. It's always converting to 0. So that means, what is IN? IN is the difference of the function in the series. So this implies, right? This implies the series convergent to. So this is the difference converging to 0. Then the series converging to is going to e to the x. Okay, for any x in this interval, but these are arbitrary. When these are arbitrary, then this also true for any x. Okay. This is an arbitrary number, right? We did not even specify. This is an arbitrary. So we always have this identity. Okay. The exponential function can be represented by the power series at any number. Okay, but this power series look different when a changes. Okay, but there's the same actually the same power series. It's independent of, yeah, it's independent. In particular, right? In particular, we have if a is 0, right? E to the x is going to be, when a equals 0, is going to be x to the n. So how do we estimate the number e? We just choose the fraction number n, right? So in particular, e is almost equal to 1 plus when x equals 1, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, and you can choose as many as 1. You can say 100 factorial. Then you can let the computer to estimate, and you really get the very the number on the right hand side is a rational number, okay, right? Because every term is a fraction, okay. So, but e is irrational number, but e can be approximated by sequence of rational numbers. Yeah, how many rational numbers? Let's say infinitely, but they're countable. That's a very basic system in mathematics. So between the interval from 0 to 10, or from 0 to 1, how many numbers there? Infinitely many numbers. How many integers there? Well, just only few, right? It's between 0 and 1, only 2 integers. That's the end point. And how many rational numbers there? The same question, how many fractions there, right? Between 0 and 1. Still infinitely many, but they're countable. You can find a way to count them. We call it countable. But irrational numbers is not countable. Okay? I always try to do a comparison, like the set of all rational numbers, like the stars of or the planets or stars in the Milky Way. But the set of all numbers is just like all the stars in our universe. I don't know how to count them. I just infinitely many. Nobody lifetime can understand. Okay. What we can even see is a telescope or whatever. We only see the area. We get a larger and larger area. That's called the observable universe. Does not mean that's the universe. Really, that's only a very small portion. Okay, that portion probably only 1% of the whole universe. Who knows, right? Yeah, very tiny. Our Earth is very tiny compared to the universe. All right, so this is a good. We find out some elementary functions, okay, can be represented by power series. But actually, almost all elementary functions can represent power series. Okay. Yeah. But there are more functions which cannot be represented by power. There are more functions, okay, which are not elementary function, which are not a function we are familiar, right? But that can be expressed by power series. Okay. But the question, if we want to find the power series, this is the way we discover some of them. But that's not mean we should always repeat the same procedure to find the power series. Okay. I know this is this holds for any x, right? I know this holds for any x. So here's a question. Okay. Find the power series, because if it exists, that's unique. Power series representation for the function f of x equal to, for example, so where I have to find the function, right? Find x, x squared, for example, right? Then we cannot repeat the same procedure as we did for the right? Because you have to find the general formula, and the question is the candidate, right? The only candidate is this one, okay? At a equals 0, okay, let me try it. The only candidate is this. But then the question is how do you find the nth order derivative? Second, how do you prove this convergence? Take too much time, right? So when you ask to find the power series representation for the function, do not always use a Taylor theorem to prove that. You can use the existing result to get that. Okay? So, but we cannot easily find this formula, the nth order derivative. It's almost impossible. Okay, the question is, what is that? And then how about the convergence, right? Whether it's convergent to the given function. It's not easy. If you have to do that, you just have to go through all the steps, like what we did for the exponential function. But in this case, it's easy. The function, no matter how many times differentiate, you get the same. You get the same function. So we give up the idea. Same idea as Taylor used. I'm going to just use the Taylor's result. Okay, modify it. Okay, so we cannot find this, right? So what I'm going to do is I'm going to use a formula, right? I'm going to use this formula to find. Okay. Okay, I'm going to use this formula. Okay, what I'm going to do is we get f of x equal e to the x squared. Just replace x by x squared. So it is going to be x to n. That's it. Simple. And this is a power series. It's not only equal that, it's convergent to the function, right? That, just one step. Okay. So it's not only convergent, it's also equal to the convergent to the function. Okay, but if you want to use the Taylor's idea, repeat the same process, just like, if you have to find a derivative, right? You know how to use the definition. But we already find the derivative sine, cosine, all components. You don't need to repeat the same definition that you use a limit to find the derivative. You can just use those results already in the formula to find the derivative. It's the same here. If you already find the power series for e to the x, then you can use that to find the power series for e to the x squared. Even the following one, okay? Find the power series representation for the function 2 to the x at at a equals 0 or at a equals 1, doesn't matter. Okay. Then you say, okay, I put 2 to the x, right? 2 to the x. All right, 2 to the x. Now, it's similar to e to the x, but it's not like that, right? You have to modify it. 2 to the x equals e to the natural log 2 to the x. How about like that, right? Then it's going to be e to the x natural log of 2. Then this is a very similar function again. Okay, and we know that this can be expressed in the form n factorial, and this part should be here, right? X natural log of 2 to the power n. Okay, and this holds for any x less than this equal, right? But this is true for general x. So the answer will be, okay, good. This power series at equals 0 is not only convergent, it is convergent to the function. Now, let me emphasize the definition here. So, definition, okay. For a differential function, for a differentiable function f of x at a, its Taylor series, because it's associated with the function. Its Taylor series is defined by this candidate. Its Taylor series at a is defined by this candidate. Okay. Yeah, we just simply call it the Taylor series. Okay. So if I ask you to find the Taylor series, how do you find it? There are a couple ways to do. One is just, you don't need to prove it's Taylor series convergent to the function, but this is just a candidate for the power series representation. Okay. So we have to use the following fact. Okay, we already mentioned that. Okay. If f of x is going to be identical, equal to this for some a is positive, then this is a Taylor series. At a. Why? Well, that's what we proved, right? So to find a Taylor series, two different ways. One is just use the definition, find all the derivatives, and figure out the pattern for the nth order derivative. Then you confirm the Taylor series. Another way to do it is, if you already know the power series representation for the function, that power series representation is the Taylor series. Because Taylor series is just the candidate for the power series representation. If you already find them, then that's it. You don't need to find so many derivatives to get the test. So if we put a problem on the test, I find out that half of students still to differential function many times and still couldn't figure out the pattern, and then here's my Taylor series, only listed 4 terms. That's incomplete solution. But that's a quick way to find the Taylor series. Okay? For example, here's a, and sometimes if you find the derivative, it's almost impossible. Okay? So yeah, so let's say let f of x to be 3 plus 2x. Okay? For example, right? And this is right. Find the Taylor series for the function f of x at a equals, right? A equals 2, a equals 3, a equals -1. Really doesn't matter. A equals -1, right? For example, that the function is defined at -1. Now, if you want to find Taylor series, the formula is that by definition, the Taylor series is going to be this. Minus -1 plus 1 to the end. My question is, are you able to find the general formula for the nth order? No, it's too complicated. Yeah, you can figure it out, right? You can do like that. Okay, let's see f of x equals 3 plus 2x to the -1. I'm trying, but many students don't have this capability to figure out general pattern. Yeah, then multiply by 2. Okay, let's continue. Okay, then you get a -1 times -2, 3 plus 2x to -3, then have another 2 square, right? Maybe you can find a pattern, okay? Let's continue. So don't multiply them out. If you multiply them, you don't see the pattern, okay? So the third derivative is going to be -1, -2, -3, 3 plus 2x to the -4, and the 2 and 2q. So I guess the case order derivative will be -1 times -2 and times -k, right? And 3 plus 2x to the -k plus 1 and the 2 to the k. Yes, but you have to figure out from few examples, make a conjecture. And then how can I write -1, -2? I have to take the negative sign out. Then I have the k factorial. Then I have a 2 factorial. Then 3 plus 2x to the -k plus 1. Okay? Then I have to evaluate at the -1. 3 plus -2, so just 1. Okay? So yes, you get power series representation. You get the Taylor series. Okay, k factorial of this, and x minus 1 is x plus 1. Okay, after that is simplified, and this is going to be the answer. Okay, we're done. So you get Taylor series on the top, but that's probably not very useful. Number one, I don't know whether it's convergent or not, over which interval. If it's convergent over some interval, is it convergent to the given function? Okay, so we are far away from what we should want to know. But here we just ask you to find Taylor series. By definition, it is. Okay, by definition, it is. It's complicated. Sometimes it's difficult to figure it out. But we're lucky here right now. I did not know I can figure it out quickly. But we see the pattern and then find the answer of the derivative. It takes too much time. So I'm trying a different way. Using the fact I list under the definition. If the function is given by the power series, is equal to the power series over something around the A, then that power series is just the Taylor series representation, because we already proved that the Cn must be given by this formula. Okay, that's the reason. Okay, then you have this. That's why this is going to be the Taylor series. Okay, so let's try this. F of x equals 3 plus 2x. I want to express as x plus 1, so I'm going to let u to be x plus 1, okay? Then that's going to be 3 plus 2. What is x? X is u minus 1. So I get 3 minus 2, so it's 1 plus 2u. Okay, it's getting close. So that is going to be 1 minus negative 2u, right? Then I have to the power n. All right. So I get negative to the n to the power n and the u to the n. U is what? U is x plus 1. So and when it's whole, when u negative 2u, right? Negative 2u is less than 1. So that u is less than 1/2. So in other words, x plus 1 is less than 1/2. So this is a Taylor series. We not only know this is a Taylor series, we know this Taylor series is convergent for x satisfies this inequality, and not only convergent to the function. So we have this identity, right? 3 plus 2x. This holds for the x. So this is the Taylor series because we determine more than we need. We find the Taylor series. We find the power series representation for the function nearby -1. Okay, so this is a Taylor series. This must be the Taylor series. Okay, so it will be much easier to find more than what you need. Okay, and yeah, but I'm pretty sure if I put the same problem on the final exam, half of students will find the derivative many times, and some will make mistakes in competition, or some will only get a few terms. As a student trying to find the Taylor series representation, then you then tell me, hey, this is the Taylor series. What you get? Okay, so Taylor series is just the candidate for the power series representation of the function. You still have a lot of work to do if you want to prove that is indeed the power series representation of the function. A given function, first step was, if this function is not familiar, you cannot modify with the existing result, right? Then you have to find the derivatives, find the candidate, okay, for the power series representation. Once you find the candidate, that candidate is called Taylor series. The Taylor tells you how to prove that series is convergent to the given function, right? If you're able to prove it, then you get power series representation for the given function over some interval. Right? If you can prove it, if you cannot prove it, then just this kind of sum series, right? Which may be divergent. We don't know. It's probably still useless. Okay. So calculus will last forever. So Taylor's contribution is here. So the name is always there. But I don't know who's Taylor. Okay. There's so many people with the same That means I need a that means I need to find right? It's a 3. So n factorial x minus 3 to the n, right? This is the by definition. If the so you still have 2 ways, right? 2 different ways to solve this problem. But I prefer the second method because already familiar with natural log x, right? We're already familiar with natural log of x. So we recall that natural log of 1 minus x is going to be negative. And I think it's right. N start from 1. Yeah, when x equals 0, that's 0, right? I think this is true. All right. Yeah, this is true. Okay, so this holds only for x less than 1, absolute x less than 1. This is identity. Okay. So how can I use that to solve the problem? Well, over there it's x gives at 1 minus x. It's okay. Okay. So the Taylor series of the Taylor. No, okay, forget it. So you let u to be x minus 3. Okay. So I'm going to start to work on that. Okay, you let u to be x minus 3. Okay, my radius of convergence will be 3 now. You can see that, right? This whole line, here's 0, here's infinity, here's 3. So I hope I can find the Parsing representation for the natural log of x at 3 over the interval. Okay. So that means x equals u plus 3. Then f of x equals natural log of 3 plus u, right? Very close to that, right? You take 3 out, and you get natural log of 3 plus natural log of 1 plus u over 3. One step, close. 1 minus negative u over 3, right? Then I can apply the above formula. It's going to be minus sigma n start from 1 and negative u over 3 to the nth power. Okay. Okay, that holds for negative u over 3 less than 1. Okay, so let's write again. It's negative n star 1. So it's n negative 1 to the power n, right? And 3 to the n. And u is going to be x minus 3 to the n. And here, x minus 3 is less than 3. All right, so this is terrible. Okay, this is the function is going to be, in other words, natural log of x is going to be equal to that power series for x satisfying this equation. And this is the Taylor series. Okay, this is the Taylor series. So if you really want to write down this, yeah, this is a Taylor series. Okay, at a equals 3. And actually, if you want to look at this, is going to be natural log of 3, right? And f of n 0 of n factorial is going to be negative n minus 1 over n 3 to the power n. I can quickly write the coefficient without you find all the derivatives. Okay, this is a Taylor series. I just say where's the coefficients like that, right? I just write on the corresponding. That's perfect solution. You don't need to find the partial derivative. Don't need to find all the derivatives, right? You can get from this known result. This kind of example usually, yeah. I think that usually at least there's one problem like that on the test. Okay. So let's stop here.